Put 23 people in one room. It is more likely than not that 2 of them share a birthday. That sounds wrong, but it is true, and by the end of this chapter you can check it yourself. Welcome. We are going to learn how to put a number on chance. Hello and welcome. In this chapter we study probability. Probability measures chance with a number between 0 and 1. 0 means impossible. 1 means certain. We begin with simple counting. Then we learn deeper ideas like conditional probability and independence. After that, we learn Bayes' theorem, which helps us update what we believe when new evidence arrives. At the end, we learn expected value, the average result, and variance, which tells us how spread out the results are. Take your time. Each idea builds on the one before it. This is the plan for the whole chapter, 4 parts in this order. First, an introduction to discrete probability. Here we just count outcomes. Second, probability theory, with more general tools. Third, Bayes' theorem. And fourth, expected value and variance. Let's begin with the first one. Now we turn to the first section. We learn Laplace's classical idea. Count the outcomes you want, then divide by all the outcomes that are possible. This is the plan for this section, 3 topics. First, finite probability, where all outcomes are equally likely. Then rules for the complement of an event, and for the union of 2 events. And finally, some probabilistic reasoning, like the famous Monte Hall puzzle. Laplace studied games of chance like dice and cards. Let's learn 3 words first. An experiment is any procedure with a set of possible results. For example, rolling a die. The sample space is the set of all possible results. For a die, it is 1, 2, 3, 4, 5, 6. An event is a subset of the sample space. It is the set of results we care about. On the next slide, we see Laplace's rule for the probability of an event. This is Laplace's rule. If every outcome is equally likely, the probability of an event E is the size of E divided by the size of S in words. The number of good outcomes divided by the number of all outcomes. The size of E sits between 0 and the size of S, so this probability is always between 0 and 1. 0 means the event never happens. 1 means it always happens. Let's use the rule. An urn holds 4 blue balls and 5 red balls. You take 1 ball at random, and we want the chance that it is blue. Step 1. Name the sample space. It is the set of balls you could draw. 4 blue and 5 red make 9, so the size of S is 9. Step 2. Name the event. It is the set of blue balls. There are 4 of them, so the size of E is 4. Now the working. We begin with P of E. Every ball is equally likely, so we may use Laplace's rule. That gives the size of E over the size of S. Putting the 2 counts in, we get 4 over 9. 2 dice are rolled, and we want the chance that they add up to 7. Same 2 steps again. Step 1. Name the sample space. It is every ordered pair of dice faces. The first die has 6 values and the second has 6. By the product rule, that is 6 times 6, which is 36. Step 2. Name the event the pairs that add up to 7. 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. That is 6 pairs. Now the working. We begin with P of E. 6 good pairs out of 36. Divide top and bottom by 6. The answer is 1 over 6. In this lottery, you pick 4 digits. You win the large prize when all 4 match 4 secret digits in the right order. Step 1. Name the sample space. It is every pick you could make. Each of the 4 places holds one of 10 digits, by the product rule that is 10 to the power 4, which is 10,000. Step 2. Name the event. It is the one pick that is correct, so the size of E is 1. Now the working. We begin with P of E. One winner out of 10,000. As a decimal, that is 0.0001. Now the smaller prize. You win it when exactly 3 digits are right, so exactly 1 digit is wrong. Step 1. The sample space has not changed. There are still 10,000 picks. Step 2. Name the event. It is the picks with exactly 1 wrong digit. Step 3. First choose which place is wrong. There are 4 places. Step 4. Then choose a wrong digit for that place. 9 of the 10 digits are wrong. Step 5. The 4 places give 4 separate groups of 9 picks, by the sum rule that is 4 times 9, which is 36. We counted 36 winning picks out of 10,000. So we begin with P of E. The probability is 36 over 10,000. Divide top and bottom by 4. That gives 9 over 2,500. As a decimal, that is 0.0036. Now a real lottery. You choose 6 numbers out of 40. Step 1. Name the sample space. It is every set of 6 numbers you could choose. Step 2. The order you write them in does not matter, so we count combinations. C of 40 choose 6 is 40 factorial over 34 factorial times 6 factorial. That works out to 3,838,380. Step 3. Only one set wins, so the size of E is 1. We begin with P of E. Only one set of 6 numbers wins, so the top is 1 and the bottom is C of 40 choose 6. That bottom number is 3,838,380. As a decimal, the answer is about 0.00000026. That is about 1 chance in 4 million. Very small. Try this one yourself. Find the odds of the biggest lottery where you live. A bin holds 50 balls. We draw 5 of them in one fixed order, and no ball goes back in the bin. Step 1. Name the event. It is that one exact order, 11, 4, 17, 39, 23, so the size of E is 1. Step 2. Name the sample space. It is every ordered draw of 5 balls. Step 3. The first draw has 50 balls to choose from. The second has 49 because 1 ball is gone, then 48, 47, and 46. Now the working. We begin with P of E. Multiply those 5 numbers. The product is 254,251,200, so the probability is 1 over that. Same question, but now each ball goes back into the bin before the next draw. Step 1. The event is unchanged. It is still that one exact order, so the size of E is 1. Step 2. Because every ball is returned, every draw has all 50 balls available. Step 3. So the sample space has 50 to the power 5 outcomes. That is 312,500,000. Now the working. We begin with P of E. The probability is 1 over that number. Notice it is smaller than before, because returning the balls makes more orders possible. The complement of an event E is written E with a bar on top. It means everything in the sample space that is not in E theorem 1 says the probability of not E is 1 minus the probability of E. Let's work it out. We start with P of not E. Not E holds the outcomes left over, so its size is the size of S minus the size of E. Then we divide by the size of S. Now split the fraction into two parts. The size of S over the size of S is 1, so we get 1 minus the size of E over the size of S. And that second part is just P of E, so P of not E is 1 minus P of E. This rule is very useful. Sometimes the bad cases are much easier to count. This is where the complement rule helps. We pick 10 random bits, and we want the chance that at least one of them is a 0. Step 1. Name the sample space. It is every bit string of length 10. Each of the 10 places is a 0 or a 1, so there are 2 to the power 10 strings. That is 1024. Step 2. The event is. At least one bit is a 0. Counting those directly is hard work. Step 3. So look at the opposite event instead. The opposite of at least one 0 is every bit is a 1. There is only one such string, all ones. Step 4. So the complement has size 1. Now the working is easy. We want P of E. By Theorem 1, that is 1 minus the probability of the complement. The complement is the single all one string, out of 2 to the power 10 strings. 2 to the power 10 is 1024. So the answer is 1023 over 1024, almost certain. That matches our feeling. With 10 random bits, getting 10 ones would be a surprise. Now the rule for a union, that is, for E1 or E2. Theorem 2 tells us how to find it. We start with the probability of the union. By Laplace's definition, that is the size of the union over the size of S. For the size of a union, we use inclusion and exclusion from section 2.2. Add the two sizes, then subtract the size of the overlap. We subtract because the outcomes in both sets were counted twice. Finally, divide each of the three parts by the size of S. Each part turns into a probability. So the probability of E1 or E2 is P of E1 plus P of E2 minus P of both. Let's use the union rule. We pick a number at random from 1 to 100, and we want the chance that it is divisible by 2 or by 5. Step 1. Name the sample space. It is the numbers 1 to 100. Its size is 100. Step 2. The first event is the numbers divisible by 2. Every second number qualifies, so there are 50. Step 3. The second event is the numbers divisible by 5. Every fifth number qualifies, so there are 20. Step 4. The overlap is the numbers divisible by both 2 and 5, that is, divisible by 10. There are 10 of them. Now we can compute. We want the probability of the union. Theorem 2 gives the shape. P of E1 plus P of E2 minus P of the overlap. Now put the counts in. 50 over 100 plus 20 over 100 minus 10 over 100. 50 plus 20 is 70. Take away 10 and we have 60 over 100. Divide top and bottom by 20. The answer is 3 over 5. This is the famous Monte Hall puzzle. There are 3 doors, and behind one door is a big prize. You pick a door. Then the host, who knows where the prize is, opens a different door that is empty. Now the host asks, Do you want to switch to the other closed door? Look at the 3 doors. Pause the video here and make a guess. Then we work it out on the next slide. Let's work it out step by step. Step 1. The sample space is where the prize sits. Door 1, door 2, or door 3. All 3 are equally likely. Step 2. Your first pick is right when you chose the prize door. That is 1 door out of 3, so the probability is 1/3. Step 3. Now the host opens an empty door. The host can always do this, whatever you picked. So this action gives you no new information about your own door. Step 4. Therefore your first pick is still wrong 2 times out of 3. Step 5. And when your first pick is wrong, the prize must be behind the one other closed door. So switching wins exactly when you were wrong. The answer is yes, switch. Switching wins 2 times out of 3. This puzzle caused a long public argument, so do not feel bad if it surprised you. Now we turn to the second section. Here we make probability more general, so that different outcomes may have different chances. This is the plan for this section. We start by assigning probabilities in a general way. Then the rules for complements and unions, which still hold. Then conditional probability. Then independence. Then Bernoulli Trials and the binomial distribution. After that, random variables. Then the birthday problem. Then Monte Carlo algorithms. The probabilistic method is left for the text. Before, every outcome had the same chance, but that is not always true. A coin may be bent, a die may be loaded. So we give a more general rule. We give each outcome S its own probability, P of S. 2 conditions must hold. First, each probability is between 0 and 1. Second, all the probabilities add up to 1. That makes sense. Something must happen, so the total chance is 1. This assignment is called a probability distribution. Let's assign probabilities to a coin. First a fair coin, then a biased coin where heads comes up twice as often as tails. Step 1. The sample space is small. It is heads and tails. Step 2. For a fair coin, the 2 outcomes are alike, so each one gets 1/2. Step 3. Now the biased coin. We are told heads comes up twice as often as tails. In symbols, P of H equals 2 times P of T. Step 4, and every distribution must add to 1. So P of H plus P of T is 1. 2 facts, 2 unknowns. We can solve it. Start from the total probability, which is 1. The coin must land heads or tails, so that 1 equals P of H plus P of T. Now use what we were told. Replace P of H by 2 times P of T. Collect the terms. 2 lots of P of T plus 1 more is 3 lots of P of T. So 3 times P of T is 1. Divide by 3. The probability of tails is 1/3, and heads is twice that, which is 2/3. Check. 1/3 plus 2/3 is 1. Good. This is a special distribution. If the set S has n elements, the uniform distribution gives each element the same probability, 1 over n. So this is exactly Laplace's equally likely case. For example, a fair coin has 2 outcomes, so each one gets probability 1/2. How do we find the probability of an event E in the general case? We simply add the probabilities of all the outcomes inside E, that is all. See the difference from before. We no longer assume the outcomes are equally likely. Each outcome can have its own probability, and we just add the ones we care about. Let's use the rule on a loaded die. 3 appears twice as often as each other number, and we want the chance of an odd number. Step 1. The sample space is the 6 faces. Step 2. 3 comes up twice as often as any other face. So give 3 the probability 2/7 and give each of the other 5 faces 1/7. Step 3. Always check the total. 5 faces at 1/7 is 5/7. Add 2/7 and we get 7/7, which is 1. Good. Step 4. The event we want is an odd number, that is, the set 1, 3, 5. We want P of E. The probability of an event is the sum of the probabilities of its outcomes. So we add P of 1, P of 3, and P of 5. Now put the numbers in. 1/7 plus 2/7 plus 1/7. The bottoms are all 7, so add the tops. 1 plus 2 plus 1 is 4. The answer is 4/7. Notice it is a little more than 1/2 because the loaded face is odd. Good news. The 2 rules we learned before still work in the general case. First, the complement rule. The probability of not E is 1 minus the probability of E. This is true because every outcome is either in E or in not E, but never both, so their probabilities add to 1. Second, the union rule. The probability of E1 or E2 is P of E1 plus P of E2 minus P of both. Both rules carry over. This theorem is about many events that do not overlap. Pairwise disjoint means no 2 of them share an outcome. When the events do not overlap, the probability of their union is just the sum of their probabilities. There is nothing to subtract because there is no double counting. The proof is left as an exercise. Conditional probability answers this question. Given that F happened, what is the chance E also happened? The rule is the probability of E and F together divided by the probability of F. This is the picture behind the rule. Once you know F happened, the outcomes outside F are gone. So F becomes your new, smaller sample space. You keep only the part of E that sits inside F, and you compare it with F, not with the whole of S. Let's work an example. A random bit string of length 4 is generated, and all 16 are equally likely. We want the chance it has at least 2 zeros in a row, given that its first bit is 0. Step 1. The sample space is all 16-bit strings of length 4. Step 2. Name F the thing we are told. F is, the first bit is 0. Half the strings start with 0, that is 8 of them. So P of F is 8/16, which is 1/2. Step 3. Name E the thing we want. E is, the string has at least 2 zeros in a row. Step 4. Now list the strings that are in both. They are 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and 0, 1, 0, 0. Check one that is missing. 0, 1, 0, 1 has zeros, but never 2 together. Step 5. That is 5 strings out of 16. So P of E and F is 5/16. We want P of E given F. The definition says P of E and F divided by P of F. Put the 2 numbers in. 5/16 on top, 1/2 on the bottom. Dividing by a fraction is the same as multiplying by its flip. So multiply 5/16 by 2 over 1. The 2 cancels against the 16 and leaves 8. The answer is 5/8. See that it is more than 5/16. Knowing the first bit is 0 makes 2 zeros in a row more likely. Another example, and a surprising one. A family has 2 children, and we are told there is at least one boy. What is the chance both are boys? Step 1. The 4 equally likely cases are boy-boy, boy-girl, girl-boy, and girl-girl. Each has probability 1/4. Step 2. Name F what we are told. We are told there is at least one boy. That rules out girl-girl, so F has 3 cases and P of F is 3/4. Step 3. Name E what we want. 2 boys is the single case boy-boy. Step 4. The overlap of E and F is just boy-boy again, with probability 1/4. We want P of E given F. Use the definition again. P of E and F over P of F. Put the numbers in. 1/4 over 3/4. The quarters cancel, and we are left with 1 over 3. Careful here. Many people answer 1/2. They think the other child is a boy or a girl, so 50-50. But the event we are told about holds 3 equally likely cases, not 2, so the answer is 1/3. 2 events are independent when one gives no information about the other. The test is this equation. The probability of E and F together equals P of E times P of F. So the recipe is simple. Work out the probability of E, work out the probability of F, and multiply them. If the answer equals the probability of E and F together, the events are independent. If not, they are dependent. Let's try the test on a real pair of events. Take a random 4-bit string. E is that it begins with 1. F is that it holds an even number of ones. Are they independent? Step 1. The sample space is all 16-bit strings of length 4. Step 2. Event E is the strings that begin with 1. The other 3 bits are free, so there are 8. The probability of E is 8/16, which is 1/2. Step 3. Event F is the strings with an even number of ones. There are also 8 of those, so P of F is 1/2. Step 4. Now list the strings in both. They start with 1 and have an even count of ones. 1111 has 4 ones. 1100 has 2. 1010 has 2. 1001 has 2. That is 4 strings, so P of E and F is 4/16. Now run the test. Start with P of E times P of F. Both are 1/2, so we write 1/2 times 1/2. Multiply, that is 1/4. And 4/16 is also 1/4, so the product matches the probability of both. The test passes, so these 2 events are independent. Knowing the string starts with 1 tells you nothing about whether it has an even number of ones. Let's test the 2 children events. E is 2 boys, F is at least 1 boy. Step 1. Event E is 2 boys, 1 case out of 4, so P of E is 1/4. Event F is at least 1 boy, 3 cases out of 4, so P of F is 3/4. Step 2. The overlap is boy-boy again, with probability 1/4. Now the test. We start with P of E times P of F. 1/4 times 3/4 is 3/16. But P of both is 1/4, which is 4/16. 3/16 is not 4/16. The test fails, so these events are not independent. That fits what we found earlier. Knowing there is at least one boy did change the answer. When we have more than 2 events, there are 2 levels of independence. Pairwise independent means every pair of events is independent, taken 2 at a time. Mutually independent is stronger. It means every group of the events multiplies out, not just pairs but also triples, and so on. Mutual independence gives pairwise independence, but not the other way around. A Bernoulli trial is an experiment with only two outcomes. For example, a coin flip heads or tails, or a random bit 0 or 1. Each run of the experiment is one Bernoulli trial. We call one outcome success and the other failure. Let P be the probability of success and Q the probability of failure. Since only these two can happen, P plus Q equals 1. The idea is named after Jacob Bernoulli. Often we run the trial n times independently and ask, what is the chance of exactly k successes? We answer that soon. A coin is biased, so heads has probability 2/3. We want the chance of exactly 4 heads in 7 flips. Step 1. Name the trial. 1 flip. Heads is the success with probability 2/3. Tails is the failure with probability 1/3. Step 2. The sample space is every sequence of 7 flips. There are 2 to the power 7, that is 128. Careful, these are not equally likely because the coin is biased. Step 3. The event is, exactly 4 of the 7 flips are heads. Step 4. Count the patterns. Choosing which 4 of the 7 flips are heads is C of 7 choose 4, which is 35. Step 5. Each pattern has 4 heads and 3 tails. Because the flips are independent, we multiply. So one pattern has probability 2/3 to the 4th times 1/3 cubed. We want P of E. There are 35 patterns, and each one has the same probability, so we multiply the count by that probability. Now work out the powers. 2/3 to the 4th is 16 over 81. 1/3 cubed is 1 over 27. Multiply the bottoms. 81 times 27 is 2,187. 35 times 16 is 560. So the answer is 560 over 2,187, which is about 0.26. Many problems ask the same question. What is the chance of exactly k successes in n independent trials? Theorem 2 answers it. The probability is C of n choose k times p to the power k times q to the power n minus k. Read the 3 parts as how many patterns times the chance of the successes times the chance of the failures. Viewed as a function of k, this is called the binomial distribution, and we write it b of k, n, p. Let's see why the formula is true. This is the proof in 4 steps. Step 1. Name the sample space. An outcome of n trials is a list of n results, each one a success or a failure. Step 2. Take any list with k successes and n minus k failures. The trials are independent, so we multiply. P to the power k times q to the power n minus k. Every such list has that same probability. Step 3. Count the lists. We choose which k of the n places are successes, and that is C of n choose k. Step 4. Multiply the count by the probability of one list. That gives the formula in the theorem. This is an important idea with a confusing name. A random variable is really a function. It takes each outcome of an experiment and gives back a real number. Please remember, a random variable is not a variable, and it is not random. It is a rule that turns outcomes into numbers. There is even a funny story. 2 mathematicians, Feller and Doob, flipped a coin to choose the name. Feller won, and we have been stuck with the name random variable ever since. The distribution of a random variable lists each value it can take, together with the probability of that value. Think of it as a table with two columns, the value on the left and its probability on the right. Because the variable must take some value, the probabilities in the table always add up to 1. Let's build one. A coin is flipped 3 times, and the random variable x counts the heads. Step 1. There are 8 outcomes, and each has probability 1/8. Step 2. If all 3 are heads, x is 3. If all 3 are tails, x is 0. Step 3. 3 outcomes have exactly 2 heads. Heads, heads, tails, heads, tails, heads, and tails, heads, heads. In the same way, 3 outcomes have exactly 1 head. Step 4. Now collect the distribution. X equals 0 has probability 1/8. X equals 1 has 3/8. X equals 2 has 3/8. X equals 3 has 1/8. Add them. 1 plus 3 plus 3 plus 1 is 8/8, which is 1. Good. This is a surprising puzzle. How many people must be in a room before it is more likely than not that 2 of them share a birthday? Step 1. The sample space is every list of n birthdays. We assume 366 equally likely dates. Step 2. The event is, at least 2 people share a birthday. Step 3. Counting that directly is hard, so we use the complement. Let p sub n be the probability that all n birthdays are different. Step 4. Imagine people walking into the room one at a time. The second person must avoid one date, so the probability is 365 over 366. The third must avoid 2 dates, so 364 over 366. In general, person J must avoid J minus 1 dates. Start with p sub n, the probability that all n birthdays are different. Each new person must avoid the dates already taken, so each factor is a conditional chance, the chance this person differs, given that everyone before already differs. We chain those steps together by multiplying. That gives 365 over 366 times 364 over 366, and so on down to 367 minus n over 366. The answer we want is 1 minus p sub n with 22 people. It is about 0.475. That is just under 1/2. With 23 people, it is about 0.506. That is over 1/2. So 23 people are enough. Most people guess a much larger number, like 180. A probabilistic algorithm is one that makes random choices as it runs. A Monte Carlo algorithm is a special kind. It answers yes or no questions using a series of random tests. Each test gives one of 2 responses, true or unknown. If any test returns true, the algorithm stops and says true. That answer is always correct. But if every test returns unknown, the algorithm answers false. This answer might be wrong. The key point is, the more tests we run, the smaller the chance of a wrong-false answer. This is a real use of Monte Carlo algorithms, testing whether a large number is prime. It matters for RSA cryptography, which needs big primes. There's a test called Miller's test using a base b. If the number n fails the test for some base, then n is definitely composite, that is, not prime. If n passes, it might be prime, or it might be a rare composite that fools the test. The chance a composite passes for a random base is less than 1/4. So failing is the short answer, and passing is unknown. Now suppose n really is composite and we try k different bases. The chance it slips past every one of them is less than 1/4 to the power k with 10 bases. That chance is less than 1 in a million. Read the statement carefully. It says how rarely a composite number fools us. It does not say how likely a number that passed is composite. Those are different questions, and the next section shows why. Now we turn to the third section, Bayes' theorem. It is a rule for updating a belief after we see new evidence. This is the plan for this section. First we state and derive Bayes' theorem. Then a generalized version for many cases. Then we apply it to build a span filter. The artificial intelligence applications are left for later study. Why do we need Bayes' theorem? Often we know one conditional probability, but we want the reverse one. For example, a medical test comes back positive 99% of the time when a person is sick, but the patient wants the reverse, the chance of the disease, given a positive test. The same question comes up for a negative test. These two numbers can be very different, and Bayes' theorem connects them. It is used in medicine, law, engineering, and artificial intelligence. This is Bayes' theorem. It gives the probability of f given E. Using the reverse probability, E given f, look at the small print. The evidence E must have some chance of happening, and f must be neither impossible nor certain, so that both conditional probabilities make sense. Look at the parts. P of f is called the prior. It is what we believed before any evidence arrived. P of E given f is called the likelihood. It says how well f explains the evidence we saw. The top multiplies those two. The bottom adds the same product for f and for not f, so the bottom is the total probability of seeing the evidence at all. The rule is named after Thomas Bayes. Let's use it on a concrete problem. Box 1 holds 2 green and 7 red balls. Box 2 holds 4 green and 3 red balls. Bob picks a box at random, then a ball at random from it. The ball is red. What is the chance it came from box 1? Step 1. Name the evidence. The evidence E is that the ball we drew is red. Step 2. Name the event we are asking about. F is that the ball came from box 1. Step 3. Write the prior. Bob picks a box at random, so before seeing the ball each box has probability 1/2. Step 4. Write the likelihoods. Box 1 has 9 balls and 7 are red, so the chance of red from box 1 is 7/9. Box 2 has 7 balls and 3 are red, so the chance of red from box 2 is 3/7. Step 5. What we want is the reverse, the probability of box 1 given a red ball. We want P of f given E. Bayes' theorem gives the shape, likelihood times prior on top, and the total probability of the evidence on the bottom. Now put the 4 numbers in. 7/9 times 1/2 on top. On the bottom, that same product plus 3/7 times 1/2. The top is 7/18. On the bottom, 7/18 plus 3/14 is 38/63. Dividing gives 49/76, about 0.645. So a red ball makes box 1 more likely than not. That makes sense. Box 1 is the redder box. Let's derive Bayes' theorem step by step. Step 1. We start from the definition of conditional probability. The probability of E given f is the probability of E and f divided by the probability of f. Step 2. Now write the same definition with the letters swapped. The probability of F given E is the probability of E and F divided by the probability of E. Step 3. Look at the tops of the two fractions. They are the same. The probability of E and F, that shared piece, is the key that links the two conditional probabilities. Start with P of E given F times P of F. By the first definition, that product is exactly the probability of E and F. And by the second definition, the probability of E and F is also P of F given E times P of E. So the two ends are equal. Divide both of them by P of E, that gives a clean formula. P of F given E equals P of E given F times P of F divided by P of E. We are almost done. Only the bottom still needs work. Last step. We must rewrite P of E. Every outcome of E is either inside F or outside F, so E splits into two pieces that do not overlap. We start with P of E. The two pieces do not overlap, so their probabilities simply add. Now use the definition of conditional probability on each piece. The first piece is P of E given F times P of F. The second is P of E given not F times P of not F. Put that sum into the bottom of the formula from the last slide, and we have Bayes' theorem exactly as we stated it. The derivation is done. This is a famous and surprising example from medicine. A rare disease affects one person in 100,000. If you have the disease, the test comes back positive 99% of the time. If you do not have the disease, the test comes back negative 99.5% of the time. We want two answers. First, if your test is positive, what is the chance you really have the disease? Second, if your test is negative, what is the chance you really are healthy? Many people expect the first answer to be high. Let's find out. Before touching the formula, we write down every number and give it a name. Step 1. D is the event that the person has the disease. Step 2. E is the evidence of positive test. Step 3. The prior. One person in 100,000 has the disease, so P of D is 0.00001. Then P of not D is 0.99999. Step 4. The likelihoods. If you have the disease, the test is positive 99% of the time, so P of E given D is 0.99. The other 1% is a missed case. Step 5. If you do not have the disease, the test is negative 99.5% of the time, so a false alarm has probability 0.005. Step 6. What we want is P of D given E, the chance of disease after a positive test. We want P of D given E. Bayes' theorem gives the shape, likelihood times prior on top, and the total chance of a positive test on the bottom. Now put the numbers in. 0.99 times 0.00001 on top. On the bottom, that same product plus 0.005 times 0.99999. Work out both products. The top is 0.00000099. The false alarms give just under 0.005, which we round. That number is far bigger than the top. Dividing, we get about 0.002. So after a positive test, the chance of really having the disease is only about 0.2%. Why is the answer so small? Let's count real people instead of using symbols. Imagine we test 100,000 people. Step 1. About one of them actually has the disease, and the test finds that person almost always. Step 2. The other 99,999 are healthy. Step 3. 0.5% of that huge healthy group gets a false alarm. 0.5% of 100,000 is about 500 people. Step 4. So among everyone who tests positive, about 1 is real and about 500 are false alarms. That is the whole story. A very rare disease plus even a small false alarm rate gives mostly false alarms, so do not panic at a single positive result. Ask for a second, different test. Now the second question, for a negative test. Step 1. This time we want P of not D given not E, that is, the chance you are healthy given that the test came back negative. Step 2. The priors are the same as before. Almost everybody is healthy. Step 3. But now we need the likelihoods for a negative result. If you are healthy, the test is negative with probability 0.995. If you have the disease, a negative test is a missed case with probability 0.01. We want P of not D given not E. Bayes' theorem again, with bars on the letters this time. Put the numbers in. 0.995 times 0.99999 on top. The bottom adds 0.0, 1 times 0.00001. That second term is extremely small, so it hardly changes the bottom. The answer is about 0.9999999. Take that away from 1, and the chance you do have the disease after a negative test is about 1 in 10 million. So a negative test is very reassuring, even though a positive one meant little. The version we saw splits the world into 2 cases, F, and not F, but sometimes there are many cases. The generalized theorem handles that. Suppose the events F1 through Fn are mutually exclusive and together cover the whole sample space, and each of them has some chance of happening. Then the chance of Fj given E has the same shape as before. The top is the likelihood for Fj times its prior. The bottom is the sum of that product over all the cases. Again, the bottom is just the total chance of the evidence. The proof is left as an exercise. Now a real application, filtering spam email. We start with 2 piles of old messages. Pile B is spam. Pile G is good, non-spam email. We choose a word, and call it W. We count how many spam messages contain it, and how many good messages contain it. Then P of W is the fraction of spam messages that contain the word. And Q of W is the fraction of good messages that contain the word. A word common in spam but rare in good email is a strong clue. Let's set the spam filter up the same way we set up the medical test. Step 1. Name the event we care about. S means the message is spam. Step 2. Name the evidence. E means the message contains the word W. Step 3. Choose a prior. To keep this simple, we assume a message is equally likely to be spam or good, so P of S is 1/2. If you know how common spam really is, you can use a better number. Step 4. The likelihoods are the 2 fractions we counted, P of W for spam and Q of W for good email. Now turn the counts into a spam score. We want the probability of spam given the word. Bayes' theorem gives that probability. Because the prior is 1/2, every term on the top and the bottom carries the same factor of 1/2, so it cancels. The formula gets much simpler. Finally, replace the two conditional probabilities with the estimates we counted. We write the result R of W, it is P of W, divided by P of W plus Q of W. This R of W is our spam score for that word. If it is above a threshold we choose, we call the message spam. Let's try a real word, Rolex. It occurs in 250 of 2,000 spam messages and in 5 of 1,000 good ones. Our rejection threshold is 0.9. Step 1. Count the word in the spam pile. So P of Rolex is 0.125. Step 2. Count it in the good pile. So Q of Rolex is 0.005. Already you can see the word is 25 times more common in spam. Step 3. What we want is the score R of Rolex, and then we compare it with the threshold of 0.9. We want R of Rolex. The rule we derived is P over P plus Q. Put the two estimates in, 0.125 on top. On the bottom, 0.125 plus 0.005. Add the bottom, that is 0.13. Divide, the score is about 0.962. Our threshold is 0.9, so the score is above it. We mark the message as spam and reject it. One word is a weak clue. We do better using several words together. Take two words, W1 and W2, with events E1 and E2. We assume the two words turn up independently inside spam, and also independently inside good mail. That is what lets us multiply the two likelihoods on each side. Again, we assume spam and good email are equally likely. Then the score has the same shape as before, but now with products. The top is P of W1 times P of W2. The bottom adds the good email product, Q of W1 times Q of W2. The independence assumption is not perfectly true, but it works well in practice. Let's use two words, stock and undervalued. The threshold is still 0.9. Step 1. For stock, it appears in 400 of 2,000 spam messages, so P is 0.2. It appears in 60 of 1,000 good messages, so Q is 0.06. Step 2. For undervalued, P is 200 over 2,000, that is 0.1, and Q is 25 over 1,000, that is 0.025. Step 3. What we want is the two-word score, and then we compare it with the threshold. We want the two-word score. The rule multiplies the spam estimates on top and adds the good email product on the bottom. Put the four numbers in. Multiply each pair. 0.2 times 0.1 is 0.02. 0.06 times 0.025 is 0.0015. Divide. The score is about 0.930, which is above our threshold of 0.9, so we reject this message too. The idea extends to any number of words. Adding words usually sharpens the filter, but not always. A word that just repeats a clue we already have, or one we counted from only a handful of messages, can make the score worse. If we use K-words, we multiply all their spam likelihoods on the top. On the bottom, we add the product of all their good email likelihoods. The shape has not changed at all. Only the number of factors has grown. Written with the counted estimates, the score for K-words looks like this. Multiply all the p-values on the top. On the bottom, add the product of all the q-values. Including more informative words usually makes the filter sharper. We can do even better by treating some pairs of words, or some special strings, as a single unit. This is roughly how real spam filters work. Now we turn to the last section. We learn two numbers that describe a random variable, the average result, and how far the result spread from it. This is the plan for this section. First, expected value. Then its very useful linearity property. Then we use expectation to find the average case running time of algorithms. Next, the geometric distribution. Then independent random variables. Then variance. And finally, Chebyshev's inequality, which bounds how often a random variable strays far from its mean. The expected value is the average outcome, weighted by probability. The recipe is short. Take each outcome, multiply its value by its probability, then add all those products together. The result is the number you would see if you repeated the experiment many times and took the average. Let's try it on a die. Let's find the expected value of a die. X is the number that comes up on a fair roll. Step 1. The sample space is the 6 faces. The die is fair, so each face has probability 1/6. Step 2. The random variable is the number shown, so x of s is just s. Now we can do the working. We want the expected value of x. By the definition, we take each face, multiply its probability by its value, and add. Every face has probability 1/6. Every term shares that 1/6, so we can pull it out. The sum becomes 1 plus 2, up to 6 all over 6. 1 through 6 add to 21. 21 over 6 is 7/2, or 3.5. Notice the die never shows 3.5. The expected value is a long-run average, not a value you will ever see on one roll. Theorem 1 gives a second way to compute the expected value. Instead of summing over every outcome, we sum over each value r that x can take. Step 1. Group the outcomes by the value they produce. All outcomes that give the value r go into one group. Step 2. Add the probabilities inside a group. By definition, that total is the probability that x equals r. Step 3. Now rewrite the original sum group by group. Each group contributes its total probability times its shared value r, so the two sums agree. This value-based formula is often easier to use. Theorem 2 gives a very clean result. If we run n independent Bernoulli trials, each with success probability p, then the expected number of successes is simply n times p. For example, flip a fair coin 100 times and you expect 50 heads. To prove it, let x count the successes. We already know the probability of exactly k successes from section 7.2. Then, by Theorem 1, the expected value is the sum over k of k times that probability. Let's work that sum out over the next 2 slides. We start with the expected value of x. Theorem 1 turns it into a sum over the values k, each multiplied by its probability. Now replace that probability with the binomial formula from section 7.2. The awkward part is the factor k in front. There is an identity that removes it. K times c of n choose k equals n times c of n minus 1 choose k minus 1. Apply it, and the loose k is gone. We continue on the next slide. We pick up where we stopped. Every term contains an n and at least one p, so take n times p outside the sum. 1 power of p stays behind, leaving p to the k minus 1. Now shift the index. Let j be k minus 1. As k runs from 1 to n, j runs from 0 to n minus 1. Look at what is left inside. It is exactly the binomial expansion of p plus q, raised to the power n minus 1. But p plus q is 1, and 1 to any power is 1. So everything collapses to n times p. That proves the expected number of successes is n times p. This theorem is one of the most useful tools in all of probability. It says expectation is linear. Part 1. The expected value of a sum of random variables equals the sum of their expected values. This is true even when the variables are not independent, which is remarkable. Part 2. If we scale x by and add b, the expected value scales by and shifts by b. Linearity often lets us break a hard problem into easy pieces. The proof is in the text. This is a classic use of linearity. A clerk lost the claim tickets and hands the in hats back at random. How many people get their own hat? Step 1. Name the random variable. X counts how many people get their own hat. Step 2. Counting x directly is hard, so break it into pieces. Let x sub I be 1 when person I gets the right hat, and 0 otherwise. Adding all the pieces gives x. Step 3. Each person is equally likely to receive any of the n hats, so the chance of the right one is 1 over n. Step 4. So the expected value of one piece is 1 times 1 over n, plus 0 times the rest, which is 1 over n. We want the expected value of x. By linearity, the expected value of the sum is the sum of the expected values. We did not need independence here, and that is what makes linearity so handy. Each piece has expected value 1 over n. There are n people, so we are adding n copies of 1 over n. That is exactly 1. On average, exactly one person gets their own hat back, whether there are 10 people or 10,000. Another use of linearity. An inversion is a pair that is out of order. I is smaller than j, but j appears first. We want the average number of inversions in a random permutation. Step 1. Name the random variable. X counts the inversions in the permutation. Step 2. Break it up. For each pair I less than j, let I sub ij be 1 when that pair is inverted and 0 otherwise. Adding them all gives x. Step 3. For any pair, I is equally likely to come before or after j, so each piece has expected value 1/2. Step 4. Count how many pairs there are. Choosing 2 positions out of n gives n choose 2, which is n times n minus 1 over 2. We want the expected value of x. By linearity, it is the sum of the expected values of all the pieces. Every piece contributes 1/2, so we just multiply the number of pairs by 1/2. The number of pairs is n times n minus 1 over 2. Multiply and we get n times n minus 1 over 4. That is half of all the pairs, which fits our intuition. In a random order, about half of the pairs are out of order. This is a beautiful application of expected value, measuring how fast an algorithm runs on average. The sample space is the set of all possible inputs. The random variable x gives, for each input, the number of steps the algorithm takes. We assign a probability to each input, describing how likely it is. Then the expected value of x is the average number of steps. That is the average case complexity. Let's apply this to two algorithms, linear search and insertion sort. Let's start with linear search. It scans the list from the start, checking each element until it finds x or reaches the end. We want the average number of comparisons. We assume the probability that x is somewhere in the list is p, and if x is in the list, it is equally likely to sit at any of the n positions. Look at the pseudocode. The while loop does the comparisons. Let's count them on the next slide. Step 1. Name the sample space. There are n plus 1 input types. Either x sits at one of the n positions or x is not in the list at all. Step 2. If x is at position I, the loop runs I times and each round makes two comparisons plus 1 at the end. That is 2I plus 1. Step 3. If x is not in the list, the loop runs all the way through, using 2n plus 2 comparisons. Step 4. Now the probabilities. The chance x is in the list is p, and inside the list every position is equally likely, so each position gets p over and the chance x is missing is q, which is 1 minus p. We want e, the average number of comparisons. Take each case, multiply its comparison count by its probability, and add. Position 1 costs 3, position 2 costs 5, and so on up to 2n plus 1, each with probability p over n. Then the missing case costs 2n plus 2, with probability q. Every term in the first group shares the factor p over n, so take it out. Inside the bracket is the sum of the odd numbers from 3 to 2n plus 1. That sum is n plus 1, all squared minus 1. And n plus 1 squared minus 1 is n times n plus 2. The n cancels, leaving p times n plus 2, plus 2n plus 2 times q. Let's read off some special cases, starting from the formula we just found. First, if x is always in the list, then p is 1 and q is 0. The average is n plus 2 comparisons. Second, if x is in the list half the time, the average is 3n plus 4 over 2. Third, if x is in the list 3/4 of the time, the average is 5n plus 8 over 4. And last, if x is never in the list, then p is 0 and q is 1, and the average is 2n plus 2. That is the worst case. All of these grow linearly with n. Now insertion sort. It builds a sorted list one element at a time. At each step it takes the next element and slides it left into its correct place among the already sorted elements. We want the average number of comparisons. Look at the pseudocode. The inner while loop is what does the comparing. On the next slide, we set up the random variables. At step I, insertion sort puts the ith element into its place among the first I minus 1 sorted elements. Step 1, name the random variable. X is the total number of comparisons used to sort the list, so its expected value is the average we want. Step 2, break x into pieces. Let x sub I count the comparisons needed to insert the ith element after the first I minus 1 are already sorted. Adding these gives x. Step 3, for one insertion, the sample space says where the ith element ends up. It can land at any of the first I positions. Step 4. For a random ordering, every landing place is equally likely, so each one has probability 1 over I, and landing at position k means the while loop made k comparisons. First, we handle one insertion. We want the expected value of x sub I. By the definition of expected value, we add each position's probability times its cost. Every position has probability 1 over I, and position k costs k comparisons. The sum of 1 up to I is I times I plus 1 over 2. The I on the outside cancels 1 I inside, leaving I plus 1 over 2. So inserting the ith element costs about half of I comparisons on average. Now add the pieces together. We want the expected value of x. By linearity, the total is the sum from I equals 2 to n of I plus 1 over 2. Shift the index. Let j be I plus 1, then j runs from 3 to n plus 1. The sum from 1 to n plus 1 is n plus 1 times n plus 2 over 2. We only want from 3, so subtract 1 and 2, that is 3. Multiply out and tidy. The result is n squared plus 3n minus 4 over 4. The leading term is n squared over 4. So the average case complexity of insertion sort is big theta of n squared. The geometric distribution describes weighting for the first success. If each trial succeeds with probability p, then the chance the first success comes on trial k is 1 minus p to the power k minus 1 times p. Read it as k minus 1 failures, then a success. Theorem 4 gives a very simple mean. The expected number of trials until the first success is 1 over p. If a trial succeeds 1 time in 10, you wait about 10 trials. A coin comes up tails with probability p. How many flips do we expect before the first tails? Step 1. Name the sample space. We stop as soon as we see tails, so the outcomes are tails, heads, then tails, heads, heads, tails, and so on. Step 2. Name the random variable. X is the number of flips we made, so x of tails is 1, x of heads tails is 2, and so on. Step 3. Recognize the shape. Outcome number k has k minus 1 heads and then a tails. That is exactly the geometric distribution with parameter p. Step 4. So theorem 4 applies, and the expected number of flips is 1 over p. If p is 1/2, we expect 2 flips. We can also speak of independent random variables. X and Y are independent when, for every pair of values, the chance that X equals the first value and Y equals the second is just the product of the two separate chances. Look at the words. This must hold for all values, not merely for one lucky pair. In other words, knowing X tells us nothing about Y. Theorem 5 gives a useful consequence. For independent random variables, the expected value of their product equals the product of their expected values. Be careful, without independence this multiplication rule can fail. The proof is in the text. The expected value tells us the average, but it does not tell us how spread out the results are. For that we use the variance. First, the deviation at an outcome is the value minus the mean. Some deviations are positive and some are negative. If we just averaged them, they would cancel out, so we square them first. The variance is the weighted average of those squared deviations. The standard deviation is the square root of the variance, which brings us back to the original units. Theorem 6 gives a handy shortcut. The variance equals the expected value of x squared, minus the square of the expected value of x. We use that shortcut in both examples next. What is the variance of a Bernoulli variable? X is 1 on a success and 0 on a failure. Step 1. Success has probability p, so the expected value of x is p. Step 2. This is the trick. The variable is only ever 0 or 1. 0 squared is 0, and 1 squared is 1. So x squared is the very same variable as x. That means the expected value of x squared is also p. Now we have both pieces the shortcut needs. We want the variance of x. Theorem 6 says the variance is the expected value of x squared minus the square of the expected value. Both expectations are p, so we get p minus p squared. Take p out of both terms. The variance is p times 1 minus p, which is p times q. Now the variance of a die. X is the number that comes up on a fair roll. Step 1. We found the mean of a die earlier. It is 7 halves. Step 2. Now we need the expected value of x squared. Square each face, then take the average. 1, 4, 9, 16, 25, and 36 add to 91. Divide by 6 and we get 91/6. Now we have both pieces. We want the variance of x. Theorem 6 again. The expected value of x squared minus the square of the expected value. Put the two values in. 91/6 minus 7 halves squared. Put both over 12. 91/6 is 182/12, and 7 halves squared is 49/4, which is 147/12. Subtract. The variance is 35/12, about 2.92. Variance has its own addition rule, called Bernoulli's formula. For independent random variables, the variance of a sum equals the sum of the variances. See the difference from expectation. Linearity of expectation works for any random variables at all. Here we need more. Independence is what guarantees the sum rule, and without it the rule can fail. The formula is named after Bernoulli. Let's use it on Bernoulli Trials. Now find the variance of the number of successes in n independent Bernoulli trials. Step 1. Name the random variable. X counts the successes, and we break it into one indicator per trial, exactly as we did for the expected value. Step 2. We already worked out the variance of one indicator. It is p times q, and the trials are independent, so Bernoulli's formula applies. We want the variance of x. The trials are independent, so Bernoulli's formula lets us add the variances. Each of the n pieces contributes p times q. So the total variance is n times p times q. Compare this with the mean, which was n times p. Chebyshev's inequality connects the variance to how often a random variable strays far from its mean. It says the probability that x is at least r away from the mean is at most the variance divided by r squared. Read it like this. A small variance means large deviations are rare, and the bound holds for every random variable, whatever its distribution. That is what makes it so useful. The result is named after Pafnuty Chebyshev. X counts the tails in n tosses of a fair coin. How likely is x to be at least the square root of n away from its mean? Step 1. This is a Bernoulli count with p equal to 1/2, so the mean is n over 2 and the variance is n over 4. Step 2. Choose the distance. We take r to be the square root of n. Now we have everything Chebyshev's inequality needs. We start from the probability we want to bound. Chebyshev's inequality bounds it by the variance over r squared. Now put the numbers in. The variance is n over 4 and r squared is n. The n's cancel, leaving 1/4. So whatever n is, the number of tails is at least the square root of n away from the mean no more than one time in 4.